Imagine a car turning a corner. Not drifting, not sliding, just turning. Now here's the strange part. For over 100 years, every single car on the road has relied on a hidden mechanical compromise just to make that simple motion possible. A compromise made of steel gears, spinning shafts, and oil-filled housings. A compromise we were told was essential, necessary, unavoidable. But what if that wasn't true? What if the differential, one of the most fundamental components in automotive engineering, was never a perfect solution, but a workaround? And what if, for the first time in history, we no longer needed it at all? Today, we are not just looking at a new drivetrain. We are uncovering why one of the oldest mechanical principles in the automotive world is quietly disappearing. To understand why this matters, we need to go back to the very beginning of the automobile, because the problem the differential was designed to solve is surprisingly simple. When a car turns, the outer wheel has to travel a longer distance than the inner wheel. It's basic geometry. If both wheels were forced to spin at the same speed, one of them would have to slip, drag, or lose traction. And that's exactly what early vehicles did. They struggled, tires scrubbed across the road surface. Steering felt unstable. Components wore out rapidly. So engineers introduced a brilliant piece of mechanical logic, the differential, a system of gears that allows two wheels on the same axle to rotate at different speeds while still receiving power from a single source. Elegant, mechanical, and for its time, revolutionary. It solved a fundamental physics problem using nothing but metal. No sensors, no computation, just pure geometry translated into steel. And for decades, this design became untouchable. As the automotive industry evolved, so did the differential. Open differentials became limited slip systems. Clutch packs were introduced. Torque biasing systems improved traction. Brands like Porsche engineered incredibly advanced mechanical solutions. Off-road systems from Toyota refined locking differentials to handle extreme terrain. And yet, despite all this innovation, the fundamental principle never changed. Because the differential doesn't actually control torque. It distributes it, it reacts, it negotiates between two wheels based on resistance, but it never truly decides what each wheel should do. And that subtle distinction is where the entire system begins to fall apart. Because driving is not just about allowing wheels to spin at different speeds, it's about controlling how they interact with the road, in real time. And that's a problem mechanical systems were never designed to solve. So the industry kept adding complexity. More gears, more clutches, more weight, trying to refine a solution that was never truly optimal to begin with. And for over a century, that compromise was accepted as the only possible way, until something changed. Not in the mechanical world, but in the digital one. This is where the story becomes uncomfortable. Because to understand why the differential is becoming obsolete, we have to understand what it was never designed to do. The physics of turning. When a vehicle enters a corner, something far more complex than different wheel speeds is happening. Each tire generates force through a concept known as slip. Not slipping like losing control, but a controlled deformation between the tire and the road surface. This is where grip comes from. And here's the critical detail. Each wheel requires a different amount of torque, at a different speed, at every millisecond, depending on road surface, weight transfer, steering angle, vehicle speed. In other words, turning is not a geometric problem. It's a dynamic control problem. And yet, the differential was designed to solve it using static mechanics. The mechanical illusion of control. A traditional differential does one thing extremely well. It allows wheels to rotate at different speeds, but it does not control how much torque each wheel receives. That decision is not calculated. It emerges passively. In an open differential, torque flows to the wheel with the least resistance, which means if one wheel is on ice and the other is on dry asphalt, the system sends power to the wheel that needs it the least. A complete inversion of logic. So engineers tried to fix it. Limited slip differentials, clutch packs, torque biasing systems. Even advanced setups used by brands like Porsche attempt to redistribute torque based on friction and resistance. But here's the problem. They are still reacting to events that have already happened. They wait for slip, then respond. And that delay, even if measured in milliseconds, is everything. Because at high speed, milliseconds define stability. Latency, the invisible enemy. Now imagine a vehicle traveling at highway speed. At 120 kilometers per hour, the car moves over 33 meters every second. That means in just 10 milliseconds, the vehicle has already traveled. D equals V times TD equals V times TD equals V times T, which translates to over 30 centimeters of uncontrolled motion before a mechanical system can even react. That's not control. That's recovery. And recovery is always too late. This is why traditional stability systems rely on braking individual wheels. Not because it's efficient, but because it's the only way to override a passive drivetrain. They are constantly correcting mistakes, instead of preventing them. The fundamental flaw. And this leads to the uncomfortable truth. The differential is not a precision control device. It is a compromise. A beautifully engineered compromise. But still, a compromise. Because it was built for a world where computation did not exist, sensors were non-existent, real-time control was impossible. So engineers did what they could. They encoded physics into metal, and for a century, it worked. But the moment real-time computation entered the system, everything changed. Because for the first time, the car no longer had to allow differences between wheels. It could control them directly. Not after the fact, not through friction, but through pure, instantaneous calculation. And that is where the mechanical era begins to break. This is where everything changes, not incrementally, not gradually, but fundamentally, from distribution to control. For over a century, engineers tried to answer one question. How do you distribute power between two wheels? But modern electric architecture asks a completely different question. What if you never had to distribute power at all? What if each wheel generated its own? No shared axle, no mechanical link, no compromise, just 4 independent sources of torque. This is the core idea behind distributed electric propulsion, a system where each wheel is no longer a passive recipient of power, but an active participant in vehicle dynamics. And once you remove the physical connection between wheels, you remove the need for a differential entirely, because there is nothing left to differentiate. The rise of software-defined torque. In a traditional drivetrain, torque is constrained by hardware. Gears, shafts, clutches, every adjustment must pass through physical components, which means delay, friction, energy loss. But in a distributed electric system, torque is no longer mechanical. It becomes digital. Each wheel is controlled by its own inverter, its own motor controller, its own stream of real-time data. And this is where companies like BYD and Tesla begin to diverge from traditional automotive thinking, because the system is no longer asking, how do we transfer torque? It's asking, what is the exact torque each wheel needs right now? The 1000 Hertz reality. And here's where the numbers become difficult to ignore. Modern control systems operate at frequencies approaching 1000 Hertz. That means 1,000 calculations per second. For each wheel, not guesses, not approximations. Precise torque commands based on wheel speed sensors, steering input, yaw rate, acceleration vectors, road conditions, every millisecond. The system recalculates the optimal state of the vehicle, and instead of waiting for slip to occur, it prevents it. Because torque is adjusted before instability develops. This is no longer reactive engineering. This is predictive control. Torque vectoring becomes mathematics. Now consider what this enables. Instead of braking a wheel to stabilize the car, the system can apply negative torque to one wheel and positive torque to another at the same time, creating a controlled rotational force around the vehicle's center of mass. In physics, this is known as yaw moment, and instead of relying on friction to generate it, the vehicle generates it directly through propulsion. Tau equals R times F, tau equals R times F, tau equals R times F, where torque is no longer a byproduct, but a precisely engineered outcome. This is why the experience feels fundamentally different. The car doesn't correct itself. It doesn't fight instability. It simply never loses control in the first place. Efficiency through elimination. But control is only half the story. Because once you eliminate the drive shaft, the transfer case, the differential multi-speed gearboxes, you remove massive sources of energy loss. Traditional drivetrains suffer from rotational inertia, mechanical friction, fluid drag. But in a decentralized electric system, energy flows directly from battery to motor to wheel. Shorter path, fewer losses, higher efficiency. This is how some modern systems exceed 95 to 97% drivetrain efficiency, not because they improved the old system, but because they removed it. The hidden transformation. And this is the deeper shift most people don't see. The car is no longer a mechanical machine. With software layered on top, it becomes a computational platform that happens to move. The hardware still matters: motors, inverters, batteries. But they are no longer the source of intelligence. They are execution layers. The real vehicle exists in code. And once that happens, the rules of engineering begin to change. Because improving the car is no longer about redesigning parts. It's about rewriting algorithms. The moment the differential becomes obsolete. So the question is no longer, can software replace the differential? That question has already been answered. The real question is, why would you ever go back? Why rely on passive torque distribution, delayed mechanical response, physical compromise, when you can control every wheel independently, in real time, with mathematical precision? At that point, the differential doesn't evolve. It becomes irrelevant, not because it failed, but because something better finally exists. This is where the story expands beyond engineering. Because once a technology stops being just better and starts redefining how vehicles are built, it becomes an industrial problem. For legacy manufacturers like Toyota, Volkswagen, or Ford, the differential is not just a component. It is part of an entire ecosystem. Factories, supply chains, tooling, decades of optimization built around casting, machining, and assembling mechanical drivetrains. Entire Tier 1 suppliers exist solely to produce gear sets, drive shafts, transfer cases. Companies like Magna, International, and Borg-Warner have built global empires on these systems. And this is where the disruption becomes uncomfortable. Because adopting a fully distributed electric architecture is not just an upgrade, it's a reset. Meanwhile, companies like BYD approached the problem differently. They didn't try to improve the differential. They ignored it. They built platforms around high-voltage battery systems, silicon carbide inverters, independent motor control, from the ground up, which means they are not replacing legacy systems. They are bypassing them entirely. Even companies like Tesla, with dual-motor architectures, still operate in a partially transitional phase. 2 motors, front and rear, better than mechanical AWD, but still not fully independent at the wheel level. The real shift happens when control becomes granular down to each wheel, because at that point, the architecture itself changes. And this raises a difficult question for the industry. Not whether this technology works, but whether traditional manufacturers can adopt it without dismantling everything they've built over the last century. Because this isn't just about replacing parts. It's about replacing thinking, from mechanical distribution to computational control, and historically, that kind of transition is never smooth. For over 100 years, the differential was a symbol of engineering brilliance, a mechanical solution to a geometric problem, elegant, reliable, and essential. But it was also a product of its time, a time when engineers had no choice but to solve complex problems with passive systems, with gears, with friction, with compromise. Today, that constraint no longer exists, because for the first time in automotive history, the car understands itself. It measures, it calculates, it predicts, and it acts before physics becomes a problem. The differential didn't fail. It simply reached the limit of what mechanical engineering could achieve. And now, software has taken over the role it was never designed to fulfill. The car is no longer a machine that reacts to the road. It is a system that controls its interaction with reality in real time. And when that happens, some of the most iconic components in automotive history don't evolve. They disappear. The future of the automobile may not be built on better parts, but on better decisions, made thousands of times per second.